And now I'd like to introduce Wang Yu, understanding TOCTTOU in the Windows kernel font scaler engine. Thank you.
Hello everyone, my name is Wang Yu, come from China. This is my first time to presentation in English. Hope it all goes well, and thanks for your attention and patience in advance. Today, I want to share with you some of my research about Windows kernel font scaler engine. This all comes from my analysis of the zero-day vulnerability in font scaler engine, which once was used by Duqu malware. I still remember at the time I began to investigate this zero-day vulnerability. I'm really astonished. I mean it. With the analysis goes into deeper depths, I find that there are many issues worth much attention. So let's just get started. Part 1, Introduction. This is my company email address, which you could reach me. And as a background, font scaler engine is widely used by Microsoft Windows and Mac OS operating system for rendering TrueType fonts. It was first introduced in 1989. Later, to improve the performance of the Windows NT, Microsoft decided to move the engine from use mode to kernel mode. This enhancement does improve the performance, but it also brings security issues. Specifically, font scaler engine represents a significant kernel attack surface, and it's perhaps the most easily accessible point which can be reached remotely. As I mentioned 2 years ago on the Cisco 360 conference, many things make the font engine vulnerable, such as the complexity of font file format, the assumptions about the interaction between the font engine and its clients, and the existence, the font cache, and so on. So many. Among their weak points, the time of check to time of use is the most critical type, I think. And I think the following 3 or maybe 4 things are quite interesting today. At first, the design and implementation of font scaler client interface. And secondly, the vulnerability CVE 2011-3402 and assumptions in the module Win32k.sys. And BoxBone TOCTTOU problems and the new zero-day vulnerability and our new tools, which are going to be really interesting. I would explain it later. Now, let's begin by explaining why font scaler is worthy of much greater attention. I'm going to illustrate from 3 aspects: why significant, why difficult, and why worthy. Significant, I think the font engine must have components from any operating system with user interaction. And it succeeds in solving the low resolution problem in font rendering, and the difficulty lies in the complexity of font engine, which many data structure lacking details, and the TrueType font developers even strive to resolve the low resolution problem by introducing a set of instructions and a TrueType interpreter. But this engine is quite appealing from the security perspective. For example, the integration of font engine into Windows kernel greatly facilitates the vulnerability exploitation and make it quite convenient to escape sandboxes because it is in the kernel. And the second, font could be embedded into Office file, PDF file, and could be also embedded into web page. indicating a vulnerability could be exploited remotely. Okay, and next I want to talk about how I get my research started. Apart from static analysis and dynamic tracing, I still attempt to find something interesting in the disclosed Microsoft Windows NT source code. Okay, I recompiled that font engine in the disclosed source code and writing corresponding client code to make it work. We will see that. I think I have to say what I have been doing is purely out of curiosity and not in any commercial interacts at all. So I bet you all understand this. Thank you. In reversing the Win32k.sys, we found many functions with a name prefix with fs unscoped, which is exported interface for the function engine. I extracted the minimum function site, which makes the function engine work normally. There are 9 such functions, ranging from fs unscoped open font to close font. We could see also many function name prefix with fs. Many of them are just no used, abandoned by the developers. For instance, we all knew that memory space are rather expensive in 1989 when I was 5 years old. Many mechanisms trying to trade time for space are never used again. In table 3, their functions are never used again. In table 3, I gave a list of meaning of each function prefixes. Okay. And I draw a graph which you could see how this minimal working set of 9 functions works. In this, if the engine takes the rule as a server, the color of this engine could be seen as a client. Apparently, both the client and the server are inside in the module Win32k.sys. The 9 functions with exported interface are just called concurrently from open to close. Concurrently, we also find the parameter of each function are just the same, like this. Function just like the same. Okay. The red part is input parameter and the blue is output parameter. They all look the same. So it seems that we need to concentrate that to their structure in and out. Based upon previous study, DT is details. DT is WinDebug in built-in command display type. DT is the details input and output is not difficult for me. Okay, because I recompiled the source code of the leaked Windows NT4. I can show you. Oh. Okay. For example, Okay, this is the input parameter, and this is output. Oh. And even I can show you how to debug the function engine. For example, I can step into the source code of the function engine. Okay. Okay. So the basic data structures of function engine are as follows. I draw a picture. Based upon their facts, we could see that the function engine does not require the allocation of any memory themselves. All the requirements of the memory are just passed through out back to client. And it's a client who ultimately allocate buffers. The function engine just fetch their memories through input when the buffers are ready. This design might be attributed to the age when the memory is so expensive. I draw this picture. The required memories are split into 4 parts, 1, 2, 3, and 4. The 5 part is internal memory, internal data structure. We will see it later. Which are the 4 parts which are parsed as a parameter to the next step, and the function engine also maintains a compact state machine. The calling procedures by the calling procedure controlled by the state machine, and it is also quite interesting. Okay, right now. With all I showed to you, many of you might think, oh, wow, sounds great. But so what? Okay, let me make it more interesting, and we would see it more clearly. I built a small project called FSAC Engine based on the disclosed source code of Windows NT 4. I recompiled the whole font engine to a library and write some code to use it to make it work. This is going to clarify how the engine actually works. And if you want, you can find the source code of the FSAC engine on GitHub by yourself. But without the library source, you know what I mean. The demo one is change the font file. After the first character is displayed, if you want to change the font file, you must return to step 3, and this is the graphics in the left showcase the rendering of the character C with the font time.ttf, and the right side is another font file. We skip this demo because it's quite simple. As for the choosing of C, it is because it has a huge arc, quite straightforward to demonstrate the font engine's processing of complex graphics. And C is the very first character of my wife's name. I really appreciate her support to my research. The second demo is changing the transformation matrix. Okay, it's quite interesting. So if you want to display, if you want to change the point size or transformation matrix, pixel diameter or device resolution, you must return to step 4. This input, right side, this input parameter indicates that we are ready to rotate the character by tangent 14.5 degree. I will show you. A source code and here. This is rotated by 155 degree. And the second and the third is a change to display a new character. If you want to display a new character, you can change the character code and return to step 5. And this time, we change the character C to Windows logo. I believe the near side guys, or you take off your glasses, you might find this more vividly. I will show this. Okay. Okay, this logo. The last example is with or without executing the VM instructions. So if you want to convert the graphics description into an outline with or without executing the instructions, you must return to step 6. In order to improve the revise the font rendering, every character has its own set of instructions. The graph in the left showcase is improved rendering of character C, and the right side is unrevised. We could see there is some minor difference, but the virtual machine-based font revision is the essence of the TrueType font rendering. This one, left side and right side. Up until now, much has been discussed about the font scaler client interface. We could understand and fully grasp the mechanism of font engine based on the project FS engine. Now it's time for some conclusions. First, we discussed the memory allocation policy of font engine. It didn't allocate any memories. The caller of font engine is responsible for the allocation and the deallocation of memories. Second, in project FS engine, memories are allocated separately from C runtime heap. And for when 32K does this, it also has its own assumption about memory allocation, which is quite different from my approach. And I think the assumptions are quite convenient for vulnerability exploitation. We will see that. And then the value of the project FS engine lies in that I transport the font engine from Windows kernel back to the use mode. And it is where it should be. Okay, and last one. If you notice the fix released on last Patch Tuesday, you will find the CVE 2018-18-1824 vulnerability. We'll lead to your attention to nbdoc.dir. What the function font in this dir is doing just the same as FS engine. You will see that. Use IDA. Okay, and you can download the code and enjoy it. Next part, I'm gonna to talk about the vulnerability, the old vulnerability, CVE 2011-3402, and its classical exploiting techniques. There are some analysis of this vulnerability in the internet, and after go over all of them, you will find most of them just tell us there are some overflows somewhere, and cause code execution and elevation of privileges, EOP. What I did, I just bring some more questions with answers. For example, what data structure is overflowed, and why is this data structure triggering the vulnerability, not others? It's a heap overflow, right? So how heap override could be used to precisely manipulate the feed CVT count? Why is there no need to control the memory layout of the heap? And for example, what is the whole exploitation looks like, and so on. Many details left for us. In order to answer their questions, we need to take a look at the following two data structures, CG_3 and CG_4. 3 and 4 was here. Here. This is 3 and 4. Is an input parameter to step 4. It's very important data structures. CG3, this data structure layout of CG3, it's also called workspace. It's responsible for the maintenance of basic information of found engine. For instance, the coordinate description of points of the glyph. And this is the data structure layout of CG_4. It's also called private space, which is the core data structure of the fountain engine. In CG4, we could find the information like the runtime state of the TrueType interpreter and the virtual machine stack, the storage area info, and even the instructions of font program and pre-program and so on. Among of these, the field CVT count in the global.js is a read one, is a key point of our story today. In order to save time, I'm going to directly outline several essential points in an analysis this CVE. I give an answer to previous questions. The module when 32k.sys make a stronger assumption of memory allocation, both data structures CG3 and CG4. It precompute the size of their data structure and then allocate the data structure contiguous instead of reside in different part of memory heap. In memory, just like an array, it's allocated together. And another interesting assumption about CG3 is it could be reused. CG3 is required input to step 4, but for step 8, it's of no use. So reducing the CG3 could evade additional memory consumption. But the routine gets a bit component who reduce CG3 does not enforce boundary checking, which means that the override of CG3 could lead to corruption of CG4, where the story ends with exploitation with excitement. manipulation of corruption memories. Sorry. Overwrite is actually an logical OR operation. The Duqu developers could directly patch some function pointer and point to user mode tunable shellcode, but they did more. They choose to indirectly corrupate the CVT count, and the corruption of this variable leads to inconsistency between actual number of CVT table and the claimed number. And then the instructions read CVT table and write CVT table, which are depend on the CVT count and table, could also generate another overread and overwrite. It's like a domino effect with a chain of overreads and overwrites. This the vulnerability part, and the next slides I'm going to describe the advanced exploitation techniques in Duqu malware. If you have ever analysis the CVE 2011-340-342, whether you have wondered what does the thousands of TrueType interpreter instruction actually do? There is thousands of instruction to trigger the shellcode. Or what is the logic of that thousands of instructions? Let's start with a simple exercise. Okay. This one. If the memory has the following layout, we try to find the value, this one, at address here. And we want to replace this value. Could you please give me a description of the searching and matching algorithm? It's group. It's a loop. Pretty simple. The three consecutive 1, 2, and 3. The three consecutive. This is a function pointer in memory are easy to spot, and all the matching could be started with this feature. Okay. And based on our project FS engine, let me give some meaning to this data. This is the crawl data structure of the TrueType interpreter. And then let me put some restriction to this exercise. Please make use of the TrueType interpreter instructions to implement your search algorithm. It's hard, right? Today we are still wondering what exactly is the TrueType interpreter instructions, but 3 years ago, the Duqu development team already gave us an answer. Compared to simple linear search algorithm, Duqu developed a trick that make use of instruction ITRP underscore flip off and flip on. This is tricky, but very interesting. It's tricky to find the location of the target data. The field local parameter block auto flip is influenced by their two seemingly unimportant instructions, and the field is here. Okay. This is the function pointer we want to search, and the field here, auto flip, is influenced by their two instructions. So the trick is when the loop around and around, around one is just like this. First, the malware executing the instruction flip off. Flip off means set to Z1 to 0, and the second use the first override to fetch the value of A. A is the first of the address. Now A is equal to 0, and then flip on. Flip on means set to 1, and later a second read fetch from the value of B. The B is also equal to 0. So the logic is the set 0, read, set 1, read, and this round A is equal to B. And the next round, set 0, read, set 1, read, so the A is also equal to B. And round 3, 4, 5, but round 17.8, around 17.8. Oh, no, not 17.8, 38. When it's flip off, set to 0, and read A, now A is 0, and set to flip on, set to 1, but this time B is 1, and A is not equal to B. So Duqu team use this trick to enable code to know exactly when it has reached the location here. And then we are close to the target. So then we could check whether there are 3 consecutive function pointer. This method turns out to more stable than other linear methods. Detection of 3 consecutive function pointer is implemented upon the subtraction instruction. And the exportable code will read 3 addresses in and check if they are 0 or not. And the end of the search algorithm, the instruction itrp on the right CVT table conducts the object hook or object hedge, and the itrp on LSW triggers the kernel shellcode, which completes the exportation. Now let's summarize the complete exporting of this CVE. First, the attacker put the overread index into the storage area, and the second, flip off, set some bit 0. And then first overread to get the value of the address CVT table sum of site index, and then and 4 set the flip to 1 and read the value of B again. If the B and the A are not equal, it means need to index plus and return to step 1. If they are not equal, it means that we are close to the target. Then we can start to search for 3 consecutive features. And 7, orderly read the values and check if they are what we are looking for. Last one, find the target. We find the target and object hedge and privilege execution. I want to say there is the whole story behind more than 1,000 instructions. What is a wonderful story, and it happens 3 years ago. the complete process from overwrite to exploitation of the vulnerability is as follows. The memory usage assumption and the reuse of CG3 and the absence of binder checking lead to the overwrite. The first overwrite, and the first overwrite leads to a second overwrite. The second overwrite, the Duqu team makes use of the TrueType instructions to conduct a signature-based search, and the shellcode copy into kernel with a heap with read, write, and RWE. So we can use the TrueType instruction to do the object handshake, and later and finally escalation of privilege. I want to say the fact and the knowledge in this vulnerability just open a door for a new world for me. It's amazing. And then analyzing the vulnerability, this CVE, another facts are surfaced. All the data reading the font engine come directly from the use mode memory. I think that's the consequence of moving font engine into kernel mode. We knew that the kernel should be more careful when reading use control data. Being cautious is never enough, especially the TOCTTOU problems. I will discuss this issue later in next section. Okay. The TOCTTOU stands for time of check to time of use. And the OS kernel or driver develops definitely would be very careful when accessing data submitted from use mode application. Otherwise, the read or write operation without checking could lead to information leaks or elevation of privilege, EOP. When the kernel is reading or writing use mode data, the use mode thread could arbitrarily modify the very same data. So the kernel is required to evade any data inconsistency, and the standard way is conducting the probe and capture. This is a Microsoft standard way to probe and capture. Probe and capture at each level inputs from use mode application. And there are some blog on MSDN. I draw a picture. Let's use this picture to illustrate the TOCTTOU problem on font scaler. The interface FSAC, okay, it's here. FSAC routine. FS routine in the font engine will directly read use mode font data through callback. That means the function needs to be aware of what themselves are doing here. Otherwise, it will lead to consequence. Okay. And as to the problem of TOCTTOU, I have to mention another awesome work called BoxBone from Google, which is already presented in CSCAN and the Black Hat conference last year. BoxBone take advantage of well-known box PC monitor to monitor the use mode memory access behavior in the specific branch of OS kernel. In series, all recorded double fetch is inaccessible. Using this powerful tool, lots of zero-day has been discovered, among which many are double fetch 0-day in font engine. I want to take this CVE as an example to simply explain what happened behind this vulnerability. Okay, the while loop is here. The while loop. The while loop inside the function FSAC compute mapping depend upon the user-controlled data. And in the loop, each cycle of execution means read some user data, which is quite inaccessible. It will lead to overflowed or out of abundance, and so on. These behaviors could be detected by BoxBone, and great job. But after excitement, we need to ask ourselves, what had left behind for BoxBone? Okay. What is left for us? What is left for 99%? I'm gonna lose my job, or any new idea. Through a long time thinking over their issue, I come up with the following answer, which are: first, find the difficult to cover code path for BoxBone, and second, find a new pattern of vulnerabilities that are unable to discover by BoxBone. Okay, and that is the mentioned in BoxBone's feature works. Is also mentioned in BoxBone's feature works. And this match, I submitted 4 vulnerabilities to MSRC, and I promised to not disclose any function details and code stack informations. So I only talk about some principles behind their vulnerabilities. And BoxBone is triggered by input data, so this could provide us the chance to reach the code recovery. After the IDA, I found something interesting, which is logical as follows. I find the engine first fetch some data from use mode and computes the size of that data. And then the kernel allocates memory with size from heap. Secondly, and then the engine double fetch and recomputes the size to initialize the kernel heap. Apparently, this kind of logic is buggy. If there are any inconsistency between 2 fetch operands, it will lead to the heap overwrite. I draw a map to make it. I draw a picture to make it clear. As this picture, the first fetch to guide size, and then the kernel or the engine allocate the size from kernel heap, and then the second fetch, it recomputes the size again and initialize the kernel pool. But if any inconsistency between the first fetch and the second fetch, first fetch and the second fetch, it will lead to the heap overflow. Okay, we will skip this demo because it's quite simple. Another is really interesting. The binary audit afterwards led me to another interesting problem, which is logical as following. The problem, so-called the font cache mechanism, has been introduced into Windows kernel to speed up font rendering from Windows XP. But the developer of this font cache, of this feature, did not realize the operation afterwards are directly accessing use mode control data. It's a nightmare to see any inconsistency between the kernel cache and the use mode control data. It's a wholly new kind of vulnerability pattern, and the vulnerability is a variant of double fetch. I think the pattern is first fetch from kernel, and the second fetch from use mode control data. And BoxBone has not find them simply because there are no expected second time fetch operations. I draw a picture to illustrate this problem. The first time the engine fetch from the kernel mode cache and allocate memory from kernel heap, and the second time fetch from the use mode controlled font file format. And if there is consistency, it means heap override. Okay, I will show this. Microsoft will fix these vulnerabilities 5 days later, patch Tuesday. Okay. The EX means that it's user mode controllable. And its consistency from kernel cache and the use mode. So when I go, it's a heap overwrite. Okay, it's a heap overwrite at the address. Okay, I also want to introduce our new tools, Duqu. My friend and our team to write this tool based on hypervisor to implement some software level feature extensions, like Intel SMAP. We call it SMAF. It means supervisor mode access filter. It could monitor a specific thread, such as the memory access behavior. And here are some of the original log. Okay, this is a core stack about I/O query file. At first, it's KI fast core entry, and the memory kernel access user mode memory is logged. For example, the one is copy from user, and then IO query file. And later we know the IO query file need to capture the object name. So the red one, the blue one is the capture process, such as read the input length. This is read the input length, and this is probe and capture. Just like the BoxBone, it also faces the code coverage and the new module identify issue. So we are still working on it, and maybe possible we will talk it next year if my English is better. Okay, I think we are not lose our job in a short period of time. And there's more things need to think. For example, what does it really mean by put the engine into a kernel? Or, as I mentioned before, the kernel engine precomputes the size of this structure, CG3 and CG4. Is this the right way to do that? Because we read data from user mode controllable directly, so it works to think, and so on. Many things to worse. The end. Okay. I can find there is a demonstrate of Rosenmove. The book Sysinternal claimed that moving the GDI from use mode to kernel mode has improved the performance without any significant decrease the system stability. But 4 years ago, Black Hat Tarvis said the GDI represents a significant kernel attack surface, and it perhaps the most easily accessible remotely. So, as to which viewpoint you will support, I think you already have an answer. As a complement, I draw this graph, from which we see that many interactions between engine and font passing are quite buggy. That is, all inputs are harmful. But I want to say this is only the tip of the iceberg. Some other gray corners of this matter are not included in this presentation. And before Microsoft fix them, be mind your font engine, please. Thank you. Thank you, guys. And sorry for my bad English.